Tracer tests are used to characterize the residence time distribution in areas where reactions are taking place, either chemical reactors or perhaps in the subsurface between wells. There are two main types of tracer tests that are used, and they differ depending upon how the tracer is introduced to the system. On one hand, the tracer can be introduced as a step increase, and that's shown here on the left side where we're plotting the concentration in as a function of time. And you can see right here at this time, the input concentration steps up to C0. The output concentration is initially 0, and then we start to have a small concentration reaching the output, and then it ramps up like this, and eventually it reaches the input. This is assuming that the tracer is non-reactive. So if we have this kind of a tracer test, we can take these results and analyze them to determine the F function in a standard RTD type of analysis. And we saw how to do that in a previous video. I want to turn our attention here to this other kind of tracer test, the pulse input. And here the input is a brief pulse that is introduced into the system, and then the output has this kind of a pulse-like nature. It's kind of a spread out pulse. So it increases, reaches some maximum value, and then decreases. And so this kind of output here can be used to determine the E function in RTD analysis. And we saw earlier that the F function and the E function are related. The F function is the integral of the E function. So if we can determine one, then we can determine the other. So it's straightforward to calculate the E function from the output concentration from the pulse tracer test. Here's how to do it. This is the expression. The E function is the output concentration times the flow rate. So this is the mass that has come out of the system, and this is the total mass that has come out of the system. The integral of the output concentration times flow over the total duration of the test. And so if the flow rate is constant, then we can simplify this. The flow just simply cancels out, and we get that the E function is equal to the output concentration divided by this thing. This is a constant, and it equals the integral of the concentration over the duration of the test. Okay, so with that in mind, we can then turn our attention to calculations of the first, second, and third moments. And this is done using the approach that we've seen before, except instead of E, in the previous video we had the integral of 0 to infinity t times E, but now we're substituting for E C over this C int. And so what it amounts to is that the mean residence time is equal to this integral, where we're just integrating the output concentration times time, and then we're dividing by this integral here. And similarly, the second and third moments are determined using these formula, which look very much like the ones that are generated for the step tracer test, but instead of E here we have the output concentration and this constant. Here's an example of the pulse tracer test implemented using the geometry that we developed earlier for the matrix diffusion analysis. So this is the geometry, and these are blocks of some kind of porous material, of a rock, and there's a fracture here. There's flow that enters this end of the fracture, goes through and discharges here. And in this problem, we have diffusion that goes out of the fracture and into the matrix, and that affects what comes out the end of the fracture. So I set this problem up, and it's very similar to the one that was done earlier for matrix diffusion. I did put in this boundary probe that is a average concentration at the outflow. So I selected the outflow surface there of the fracture, and I labeled this, or I made this variable called abcout. That's the average over that surface. Then what I did was to set this up initially where the porosity was equal to a small number, 10 to the minus 4. And I have this set up here so that in the transport part of the analysis, I've got this part here is the properties of the fracture. And so I selected it there, and I'm putting 0.2 as the porosity of the fracture for the transport analysis. And that'll be important because that's what's used to go from the flux calculated by Darcy's law of physics to the velocity that's used in the transport. And okay, so let's see. Then I guess the important thing too is that under here the physics of the transport, I have this variable porosity, and that's the variable that I just showed up here. So when I change this, I'm changing the porosity of the matrix, but not the porosity of the fracture. And the reason I'm doing that is because the porosity of the fracture controls how rapidly the flow goes along the fracture. And I want to hold that constant. I'm going to change the porosity, but the porosity of the matrix, but I don't want to change the porosity of the fracture. Okay, so the Darcy's law is set up with an inlet boundary condition up here on the upstream end, and there's the velocity of or this is the flux, the inward flux of the water to e to the sixth, and the flow velocity, the average velocity of the water moving through that fracture is 2e to the sixth times 1 over porosity of the fracture. And the porosity of the fracture is 0.2, 1 over that is 5, and so 5 times 2e to the sixth is a velocity of 1 e to the minus 5. Okay, so that's going to be important because we can then use that to determine the travel time along this fracture. It's 5 meters long, and the velocity, the average velocity of the water is 1 e to the minus 5. So the travel time of the water is 5 e to the 5 seconds. Okay, so that's that's about a week. Okay, pretty slow flow going through this fracture here. All right, so we go and do the analysis, and it's done in 2 steps. We do the fluid flow and then the transport. And let's take a look at the plotting of the boundary probe here. So the average concentration out. And here it is. This is a log scale. So there's 10 to the fifth, 2, 3, 4. There's 5 times 10 to the fifth seconds. And we go and see that the concentration reaches about 0.5 when the time equals 5 e to the fifth. Well, that 5 e to the fifth is the travel time of the water. So this is how long it takes the water to go through the fracture, and we see we've got this this concentration arrives a little bit ahead of the water, and this arrives behind it, and this is a spreading of the concentration front due to dispersion within the fracture. Okay, so that all makes sense. In this case, there's the compound is traveling along the fracture, and there's very little interaction with the matrix. So we can go and do the moment analysis here, and I'm doing that with this derived values. The first thing that I'll do is use this global evaluation where I can then integrate this average C out. So I use global evaluation, I put in avc out, and I can select that here. Make sure that I'm using the right solution. And I also make sure that I'm I'm going to integrate it. So I do that, and I get the result here. Actually, let me go. There's the result. Okay, so that's the integral of C out. So I'll copy that. And now to calculate the first moment, it's the outflow concentration times T divided by that integral that I just calculated. It's this one right here. Now this is the integral for the first moment, and I substitute in that integral value that I just evaluated. And so I set this up also as a global evaluation for solution 2, the transient transport analysis, and I have that set as integral. And so I'm going to evaluate this, and there's the result. Now this is the mean residence time, and if I look back up here at the boundary conditions for the species transport analysis, the concentration on the inflow is equal to 1 times this step. And so this is this step test where well, this is actually a pulse test, and the pulse starts out right when we start the analysis, and this step 1 is the width of the pulse. So I go here to step 1, and the width of the step here is 3 e to the 7th. So that's about a year, a little bit less than a year. Okay, so in seconds. It's a big number, but we're just working all in seconds here. Okay, so we've got this square pulse of 1 year long. So there's the outflow, and you can see that it's this square pulse. And when we did the moment analysis, we get that the moment, this is the first moment, so this is the mean residence time, is 1.57 e to the 7th. Well, the pulse is 3 e to the 7th, so a mean residence time is just about half of the pulse length. And so that seems about right. That will give us a mean residence time of, let's see, 1.5 e to the 7th. So it's 1.57, which is going to be right about there. And so that seems about right. For this case, where there's no interaction between the fracture and the matrix, we have a mean residence time that's just about half of the pulse. Okay. Let's go and repeat the analysis with a new porosity. Change the porosity to 0.1 and go and revise the calculations. So I updated the fluid flow, and then I also redid the transport analysis. And the concentration coming out of the fracture now looks like this. So it increases, and instead of going up and reaching 1, which we had before with when the porosity was very low, it kind of levels out, or tries to level out, and reaches a maximum of about 0.9. And this is where we shut off the inflowing concentration, so the end of the pulse, and then the concentration drops off. But you can see it tapers off, and it's getting small, but it hasn't even really gone to 0 here at this point. So this is 10 to the 8th seconds. And what I want to do is repeat the moment calculation and come up with an estimate of the mean residence time. If I just look at it, the mean residence time is like the center of gravity, so it's going to be something right in here where this area under the curve is equal to that area under the curve, something like that. So let's go and repeat the calculation and calculate it. The first thing to do is repeat the integral of the concentration, and the thing that I need to do is it's set up by default to do the integral over all of the times in the analysis, but I ran this analysis to 10 to the 9th seconds, and I'm only interested in 10 to the 8th seconds right now because that's what's shown in my plot. So I use from list, and I select out to 10 to the 8th, and then I go to evaluate. I'm going to clear this out first, And so there's the integral of the concentrations over 0 to 10 to the 8th. And then to calculate the first moment, I go here, I'm going to cut and paste that number right here into the denominator of the term that I'm going to integrate for the first moment. And I'm going to have to adjust the time here. So we're going to go, and we're only going to integrate up to 10 to the 8th right there. So I'm going to select that and go on from there to the beginning. Now I do the evaluation, and there's the mean residence time, about 2 times 10 to the 7th. So if I look up here at this plot, I get, well, right about there. Okay, that's 2 times 10 to the 7th as the mean residence time for this plot. Okay, so that seems about right. When we did this calculation earlier, we got about 1.5 e to the 7th. So by increasing the porosity, we've delayed the arrival of the center of mass. We've delayed the mean residence time because some of the mass is diffusing out into the matrix and then diffusing back rather than just traveling along the fracture. So that makes sense. But let me show you something that is actually kind of interesting, because what I've done here is stop the analysis right here at 10 to the 8th seconds. Well, we ran this analysis out to 10 to the 9th seconds, and we're not including that information here. If I include it, then I have some tail, some concentration out here, small concentration, but it's a small concentration over quite a long time. And so that could end up moving the mean residence time out this way, making it longer. So let's just repeat the analysis and see what it gets us if we use all of the data. So this will be the mean residence time for this test that ran out 10 to the 9th seconds. And I'm just going to select all time here and repeat the evaluation. Let me do this. Yeah. And so there it is. There's the integral of the concentration, and I'm going to cut and paste that in there. And here I'm going to select all, and I'm going to evaluate this. And this is now the mean residence time if I include the tail out to 10 to the 9th seconds, and 3.6, say 3.7 e to the 7th. Well, you recall that when we chopped the analysis here and ended it, we got right about there, about 2 times 10 to the 7th. Now when we include that tail, it stretches out here about 3.6, which is right around in here. Okay, and so the reason for that is because it's a small concentration coming out, but it's doing it over a long time, and so that causes the mean residence time to move out and be a good bit longer as a result of the long tail. So that's one of the consequences of the matrix diffusion that is showing up in this analysis of the first moment.